Okay, so hopefully you can all hear me well and you can all see my screen. Just good morning. Sorry, I will mute everyone. Just as part of this, a few housekeeping rules, I guess. Like I said, I'll mute everyone just to prevent any background noise from anyone, and hopefully you won't get too much background noise from my end. At the end of this, there'll be a short Q&A session, and we'll try to keep to the time frame as well. So what I would encourage you to do is, if you have any questions throughout the webinar, please type them into the chat box, and then we can get to them at the end of this, at the end of the presentation. If we don't have time, please, again, feel free to email me at the email address shown there. I'll show it again at the end as well. And I can, liaise with you then. And I guess after this session is complete, there'll be a feedback survey coming out to you all. Should be sent tomorrow. So we encourage any feedback on our webinars to improve the way we do things. So look forward to that. But the purpose of today's webinar is to obviously explore some of the more common comminution tests that are available and how the results are applied. And I guess I'll try not to go into too much detail about the individual tests. It'll take a long time. So the next webinar basically will be on the laboratory test work itself. So if you'd like to know more about that, then please join in next month. Get ready. So a bit about me. My name is Bevin Wong. I'm the operations manager at JKTech. I've been working there since 2012, and I guess I manage a few consultants, and we sort of do a lot of work across the whole sort of production value chain, I guess you could say, from geology all the way to I guess all the processing aspects. My focus is generally around the Geomet mine-to-mill side of things, together with a lot of the test work and analysis, obviously, that we do. Get involved in a few due diligence projects. My background is mainly in operations environment and also project development. So I did a lot of work for the former Xstrata, or Glencore as it's now known, and a lot of the feasibilities that they had. I was heavily involved in a couple in Peru that had started up, namely Antapaccay and Las Bambas. And also involved in a big feasibility study at Frida River, which is a big copper project in Papua New Guinea. So yeah, look, I'm just going to go through a little bit of the marketing side of things. So JKTech itself falls under the Sustainable Minerals Institute at the University of Queensland in Brisbane, Australia. In the SMI, they lead and conduct a lot of the cutting-edge research across the whole mining value chain. When I talk about that, I mean safety, social responsibility, environment, and water. Plus two of the more sort of well-known ones around. That's the Julius Kritschnitt Mineral Research Centre and the Bryan Research Centre. So obviously doing the processing and mining and geology research respectively. So JKTech is the technology transfer company of the SMI. So we basically take a lot of the research outcomes and apply that into the industry. And we've been doing that for many years now. JKTech itself obviously commercializes, like I said, several products which have come out of the research, which are known as the benchmarks in the industry. So we'll start off with JK SimMet and JK SimFloat. They're our sort of premier comminution and flotation simulation packages that are used across all the world for design and optimization of plants. And the JK drop weight tester, which we'll get to a bit later, and that's the benchmark for comminution or characterization. Another sort of a newer one we've got out is called JK VBOC, which is a value-based ore control. That's what it stands for. That's our latest tool, which focuses on predicting blast movement within the mine to optimize dilution and grade control. Other services we provide, generally around the consulting and training activities. So again, we do that across the geology to all the way to processing aspects. And we obviously utilize a lot of the tools that are listed on the left-hand side there. But we do pride ourselves on being fully independent. We're not aligned to any vendor or engineering company or anything like that. And we utilize what we consider the best practice methodologies in all of our work. We do have our in-house laboratory, which does complement a lot of our consulting work, and obviously does all the commercial or characterization test work, mainly in the comminution and flotation space. But it is, the vast database in all the test work results and operational data that we have, collected over a many number of years. That fully underpins all that we do. So that's all for the marketing side of things. So let's get into it. Throughput is king. So as most of you would appreciate, the majority of operations, this is what stands out. Everybody always wants to increase throughput, always talking about throughput. But why is throughput king? Comminution processes are generally the most capital intensive in building a mine. The equipment there is very expensive. The OPEX as well, so the consumption of energy, mill media, mill liners often make it the most, or at least one of the most, the highest operating cost on a mine site. And all this obviously leads to making it most of the profit limiting sort of process. So when it comes to comminution circuits, we need to ask ourselves sort of the following questions. How do we size the equipment properly? And do we have enough grinding power? Because if we get this wrong, we're either not going to achieve our budgeted mill throughput, or we're going to have a pretty oversized circuit and wasted a bit of money. And most likely we'll have to spend more money in order to rectify any of those issues. Another consideration is how hard is the ore going to be tomorrow, the next week, next month, within the next 5 years, and going on through life of mine. So do you know what the ore body has in store for you? Like I say, any curveballs? So it all comes down to knowing your ore body at the end of the day. So on the screen there, just a very simple sort of deposit showing, we can separate generally into 3 distinct layers: oxidized zone, supergene, and hypergene, or the fresh material. Generally, as we do get deeper down into the deposit, it typically gets harder. Look, there's obviously a lot of other things contributing to hardness to take into consideration, but that'll be a whole different webinar. But overall, the harder the rock, the more energy required to break that rock. A couple of other things we need to take into consideration, though, within the ore body, which contributes to the specific energy requirements. Basically, how fine is the grain size of your valuable minerals? Which basically leads to how much liberation do you need to achieve to get acceptable mineral recovery, or deleterious element rejection in some cases. So you need to have a good handle on all these aspects. So what do we need to do? Well, obviously it all comes back down to ore characterization, the test work side of things, test. As, I don't know, most people on this webinar probably metallurgist or processing engineer. So, we always need to be testing all the time. that's our job. Now, there's going to be, there's a lot of tests out there on the market, and these tests are continually being created and offered by various vendors, laboratories, universities, and other consultants, etc. But most of the time, we always want to use the proven and benchmark tests that provide us with the most accurate information for whatever purpose we want for that. So in the testing space, there are the traditional, the more modern tests to consider, and within that we have the different types of tests that we use for process design and exploring variability. Again, often we refer to that as Geomet Tests, and those ones we'll look at today. And the other key thing is just to be aware that hardness, when you use that word, it does mean different things to different people throughout the mine site or whoever you're dealing with. So, for example, if you're talking with a geotechnical engineer, hardness is usually associated with the test that they refer to as the unconfined compressive strength test, which is usually used for wall stability purposes. The test itself uses full core samples, and as you can see in the picture, it's compressed to determine the capacity of that particular ore to withstand the actually directed crushing forces. So the stress and the strain is measured until that core fails, and then you get basically a reading in megapascals. And look, a lot of these studies involving the UCS, they're very good, and they supply a lot of the structural data for the mining and engineering applications for underground roof and floor studies, and also used obviously in the foundation and material testing for construction, the construction industry as well. The UCS test is also used by the drill and blast engineers to predict fragmentation of particular blasts. And they use various predictive models in order to do that, to generate all of these particle size distributions, which flow onto the crusher and the mill at the end of the day. So in this case, all hardness to a drill and blast engineer refers to, for them, it's how coarse the size distribution will be, or how many big rocks will be going towards the crusher, and how hard it is to blast. But like I said, for most of us, I think hardness will mean the resistance of rock to impact breakage and grindability. That's what we'll be going through next. So like I said, this is what the tests. So what tests do we use to do all this? So here, I've sort of broken it up into 3 general categories. I call it the bankable tests, which are mainly used, obviously, for the design of comminution circuits, the design of mills. And it's exactly what it says. It's the banks, when they do their due diligence with their technical teams, they want to see these types of tests have been done before they release their money to finance your particular project. Then we get down to the geometallurgical tests. These are, like I said, variability for variability assessment purposes of the ore body. Generally, they should not be used for design purposes. There's a lot more inherent error associated with them, but they're very useful for obviously looking at the ore type variability, ore domaining within your deposit. And some of the advantages of them are that they are cheaper and they require smaller mass. The other type of test is sort of proxy tests. I won't go through them in great detail today, but generally they're sort of used to create relationships between the ore properties and comminution attributes. And simple examples being the geochemistry data that's collected by the geologist down for every meter of core, or even mineralogy if that's collected. So all that can be classified as a sort of proxy data. So the first I guess, more common traditional tests we've developed pretty well, relatively long time ago was done by Fred Bond. He developed a whole scheme of tests in back in, I think, the 1950s, mainly for the design of crushers, ball mills, and rod mills. And look, these tests, like I said, developed a long time ago, but still used. They're very common in what we do now, only because a lot of the times there's nothing else been developed and it just works. So the most common test around is the Bon Bor Mill work index test, obviously used to determine the bond work index of an ore for ball milling requirements. And again, yeah, similar thing with the rod mill test, but not as common nowadays. The test itself is done by preparing a sample of ore to 100% passing 3.35 millimeters. And that material then goes in, can go in wet or dry, depending on the P80 you're targeting, into a standard bond mill, which is shown in the picture up on the top there. And with this is a standard number of balls, which have to be a standard size as well. It's sort of across a range of sizes. And the test itself is quite an iterative process of sort of grinding, screening, and feed replenishment until you reach steady state. Generally, it'll go through sort of seven cycles, which takes a while to do. But, you know, we get, at the end of the day, we get a bond work index result. What do we do with this result? Well, the first thing you can do is generally it's benchmarked. So, you know, the result is basically put into the following categories of soft, medium, hard, or very hard. So basically, after this test, you can say if you've really got a hard ore or a soft ore. But going further, we can use it together with Bond's equation to determine the actual specific energy required to grind this ore from a particular F80 to a particular P80 at the end of the day, using the following Bond equation. So what you do with the lab result, it just goes into there, work index. And obviously with that one, you need a target P80 in mind, together with the expected F80 of the circuit. And you will end up calculating the predicted ball milling circuit specific energy requirements. So as an example, to put things in perspective, let's just say you did a lab test and you got a bond work index of 15 kilowatt hours per ton. All you do is plug that into the equation together with in this example, a P80 of targeting 106 microns with an expected F80 of 3000 microns. And with that, you calculate 11 kilowatt hours per ton of ball milling requirements. So from this, you can basically size your mill accordingly. It must be noted, though, that the power requirement calculated here is the mill pinion power. So there is energy loss between the pinion and the actual motor that does need to be taken into consideration in any of your design calculations. So that's for design requirements. But for those of you in operations, you know, if you already have a ball mill, using this example, let's just say we've got 5,000 kilowatts of ball milling pinion power. We can calculate basically what the throughput would be for this particular ore. So basically just using this equation, this equation here, 5,000 kilowatts times by the inverse of 11 kilowatt hours per ton, which equals 455 tons per hour. So basically your ball mill will only be able to treat 455 tons per hour of this ore. So this is you know, a case where you can show your managers that the ball mill can't process the expected 500 tons per hour because the ore truly is very hard. So in this case, at least you've got some proof to the manager to be able to justify your decision. Moving on to the bond crushing test. Again, this is used to calculate the crushing net power requirement when sizing a crusher. It's still relatively widely used, I guess, but there are a couple of other methods we'll see in the following slides that you can also use to size crushers. So with Bond's method, basically you end up with obviously a crushing work index, WI, and look, you can use this to determine the required sort of open side setting of your jaw or gyratory crusher, or even and the closed side setting as well for cone crushers for a given product size. So as you can see there, just a few pictures of what it is. You're basically putting a rock between two hammers and crushing that rock. And there's an example there down the bottom of a equation for what you would do with regards to the jaw crusher. With that equation to be able to determine what open side setting you require. So there are other equations, I think, for the gyratory and cone crushers as well. Then we have the Bond Abrasion Index tests. Again, a lot of people use this for predicting the liner wear and media consumption within your mills. Again, relatively standard test. You can see in the picture there, there's actually it's a rotating mill. Obviously, you put your sample in, and then you can put different materials, paddles, they call them, which go round and round. And at the end of the day, you're just figuring out the difference, or the weight before and after of that paddle. But with the result that you're given, you basically there's a bit of a range of equations that Bond developed, I guess, based on his knowledge of wear rates for crushers, ball mills, and rod mills that are available for I guess predicting the your wear rates in your mills. So they're the Bond methods. But yeah, what do we do for ag and sag mills? We can't. It's not recommended to use the Bond method per se for designing and optimizing sag mills. A couple of the reasons, obviously, Bond developed these tests before the age of autogenous milling. And some of the key differences, obviously, as I've stated before, the Bon Bor Mill Test is conducted at 100% passing 3.35 millimeters. Very small, and as we know, sag and ag mills take the top sizes can get sometimes over 300 millimeters in some cases. But again, one of the other requirements for Bond's method is that the feed and product to particle size distributions are approximately parallel. So you can see there, most of us would know, the cyclone overflow and the crushing circuit product are generally parallel, but for sag mills and ag mills, this is not the case. So again, not recommended to use Bond's method for dealing with ag-sag mills. But this is why the drop weight tester was developed back in the 1990s at the JKMRC. So the drop weight tester comprises basically a steel drop weight that is raised and then basically falls under gravity to impact on individual rock particles. In order to impart, different energies, the height and the weight is changed, and so yeah, you'll test quite a number of particles in order to do this test. So a wide range of energy inputs to be generated. The test itself does require quite a bit of material, anywhere between 60 and 100 kilos, I guess, is recommended. And what happens is you testing 5 different size fractions across a range of those energies between 0.1 to 2.5 kilowatt hour ton impacts. And basically, the results are interpreted basically by a single point on the size distribution curve. That's what we're commonly known as the T10. I won't go to that in great detail, but that's what the research showed, the T10, which is 1/10 of the original particle size. It's also referred to as I guess the amount of breakage that's shown on the y-axis there. So yeah, basically as you break the rocks, you plot the data against the specific energy, or the amount of breakage against the specific energy applied, which results in the following sort of exponential curve, which is defined by that equation. And that is where we get the parameters of A and B from. So a lot of you would have heard of that before, but very common nowadays in metallurgical speak. So the A and B parameters, the A parameter is the maximum amount of breakage that occurs that's been achieved in the test. The B parameter is the overall slope of the curve at, I guess, the lower energies. And the A times B value is actually the slope of the curve at the origin. So basically, the larger the AB value, the softer the rock, and similarly, the smaller the AB value, the harder the ring. So you've got, have to apply more energy in order to get more breakage, obviously. From here, the results can be benchmarked again, or they are benchmarked again from very hard to very soft, according to the large database that we've got. And again, yeah, you can just leave it there as a qualitative sort of measure. Otherwise, how else do the results get used besides benchmarking? So obviously, the main use that we use is within JK SimMet. So that's just a sort of a screenshot there. So the AB properties and a few different other parameters and appearance function data that's generated as well can be used within JK SimMet to predict the sizing of requirements for Sag Mills for design type projects. Or similarly, they can be used to forecast the mill throughput and simulate any changes within the circuit to increase the throughput what can be done. Similarly, we can use the results from the drop weight tester to, in the same way for the crushers for design and optimization. Some of the other advantages there is that from an optimization point of view, you can change the shape of the feed and the product sizings as well. So not just the F80 or the P80. And we can also take into account the effect of the circulating load around that sag crusher and screen. Same thing goes for the bond work index. The bond ball or even the bond rod can be used within SimMet, again for other design or optimization purposes, and can do the same thing. One of the main things there is accounting for those changes in circulating loads. So and also the shape of the feed and product sizes as well. So the test that borders being probably between bankable and Geomet at the moment is the SMC test. So it's pretty much a more cost-effective means for profiling an ore body. And yeah, again, the SMC test is used to predict comminution circuit throughput, as well as rock mass characteristics and blasting properties overall. So it uses the drop weight tester machinery, but only tests one size fraction. So you have a big, very much reduced sample mass requirement there. So going down from anywhere between 60 to 100 down to about 30 kilos. So obviously you can, for the the same price and the same amount of mass, you can do more tests, which leads into better sort of variability testing across your deposit. The test generates a number of parameters. So the main one, obviously, it can generate the A and B parameter, which can be used within JKSimNet. It generates a drop weight index parameter, which is the measure of resistance of a sample to impact breakage. But also you get those 4 values there, the MIA, MIB, MIC, MIH. Basically for ag, sag, your ball mill, crushers, and HPGR respectively, that's what they stand for. So obviously, so obviously the test was developed by a guy named Dr. Steve Morrell, and he's got his company SMC Testing, which the link there is at the bottom. So again, what do we do with the results that you get? So as I said, you get the drop weight index, you get all the MI parameters. So for milling circuits, this is the Morrell approach to calculating the specific energy requirements, which is done generally in 2 stages. So you have a coarse and a fine breakage stage. And again, you can calculate the specific energy requirements for a comminution circuit to size or design your mills, or you can determine your throughput on your current installed power. Similar. I haven't listed all the equations used in the Morrell method. There is quite a bit. So if you do want to know more, I do encourage you to go to the SMC testing website. There are a few examples and spreadsheets there that they've got, which are quite handy. But generally, the equations there, so WA being the coarse breakage and WB being the fine breakage. I've got a couple of equations there, so it's almost very similar to I guess Bond's equation overall, but the equations there, basically X1, X2, and X3 sort of relate to the P80 and F80s. Obviously, you get the MI values from the test work. That K factor there, it just basically a parameter which basically if you indicating if you've got a pebble crusher in the circuit or not. So yeah, once you've got your WA and WB parameters, or if you've got HPGR, there'll be another equation. You can calculate that SAB specific energy requirement. I'll go through with that one. So I'll get into some of the more geometry variability tests that typically we perform as part of our Geomet style projects. So again, bankable tests used to size mills. So we've gone through the drop weight test, the SMC, and Bon tests in general. So the Geomet tests again reinforce, they're the cheaper tests, but it doesn't mean you save a lot of money. Technically, it means that you will do more tests in order to obtain a larger data set, so you get more knowledge about your deposit. Again, they're not for mill modeling or any sizing studies, but again, all about variability and domaining purposes at the end of the day. Yeah, if you do want to use them for design, you do so at your own risk. So, generally we're faced as a metallurgist, we're faced with a lot of core, and this is where obviously the Geomet and proxy tests are good for defining the ore domains. Then as you go down a bit of core, Geomet and proxy tests, you can get some really good data to show where are the harder and where are the softer domains potentially within your deposit. Further analysis, hopefully you'll be able to relate that back to an attribute, some sort of property in the ore, maybe mineralogy, for instance, to be able to get down to the true driver of why that ore is hard, or potentially why it's soft. So that's the objective of these ones. And overall, at the end of the day, the end goal is to have the hardness put back into the block model at the end of the day, so that no matter what sort of planning you're doing, short-term or to long-term planning, you know what you're going to get in your mill at any one time. So the first test I'll just go through is called the JK Bon Bor Mill Test. And look, this was a test developed due to what we saw as non-standard Bon Bor Mill work index testing being conducted throughout laboratories all over the world. So like I said before, the Bon Bor Mill test has a standard procedure, but is it really followed stringently? So JKTech, we conduct a round-robin test every couple of years to maintain the quality of our drop weight testing machines all across the globe, to make sure that they're all producing the same results, plus or minus. But one year, I think it was 2015, we also conducted a round robin on the Bon Bor Mill Test at all the laboratories who participated. So there was 40 samples tested across, I think it was about 37 laboratories in total, which includes all the majors. But what we found was that the average Bon Bor Mill work index that came back from all the labs was 15.4 kilowatt hours per ton. But with a 95% confidence interval, that was a plus or minus 2.1 kilowatt hours per ton, or equivalent to 14%. That's a pretty big difference. So with these numbers, we used just to have a look. We used the standard SAVC circuit in JK SimMet, which showed that this difference. So if you went from anywhere between a bond work index of between 15.4 to 17.5 kilowatt hours per ton, that equated to around a decrease in throughput of almost 18%. Similarly, if you look at the other way around, the model predicted that you would require an extra 30% power in your ball mill to be able to accommodate this increase in hardness to achieve the same throughput. So these are significant numbers that obviously can make or break projects at the end of the day. So all of this comes back to what we just comes back to the quality control of the tests that are conducted. So again, the mill that's being used, the standard charge, the number of balls, the size of the balls, or even the procedure. So the JK Bon Bor Mill Test, again, developed at the JK MRC using its extensive database, developed this test, which ended up being a faster, cheaper, and requiring sort of less sample as well. The good thing is that the inherent error, or the relative error, was similarly pretty much as low as the standard Bon test as well. So we're quite obviously quite happy with this test. So any lab who does provide this test is also part of the round robin quality control program, so we can be assured that every test that is done is within error. I mean, and otherwise, if you are getting a Bon Bor Mill test done, I do implore you to ensure that the lab you are using is adhering to the standard method, and ensure that lab does some sort of QA/QC on that test as well. The point load test is another test that can be used within the Geomet space with some success. Relatively simple test done. As a lot of people can do it as part of sort of geological logging in some companies. So some companies have quite large data sets of this data. Like I said there, it can often be used to predict UCS test work as well. So they usually have some sort of close alignment. But the better thing about this test is it doesn't require core. It can be used on rock samples as well. And for some clients we've dealt with, the point load test has been related back to an AB from an SMC test, for instance. So you can basically relate that to throughput at the end of the day. Generally, they show a lot higher error, but obviously that depends on your use case. So for some clients, it's obviously good enough for them. Look, in saying this as well, UCS test data is quite useful. Some sites do have a lot of this this test work data. Again, mainly from a geotech point of view. Rare, but in some cases there is a lot. And that can also be used as sort of a Geomet style test for use in interpretations as well. So it does have its place, obviously. The other test that we sort of use as well is associated with the JK Rotary Breakage tester. So this was developed as as a replacement for the traditional drop weight tester unit. It's a lot faster, has less operator error, generally cheaper to do as well. But of late, we've been using it for a particular test called the JKRVT Light test. So that's I guess a scaled down version, which uses a lot smaller particle sizes down at the 10-11 millimeter mark in order to produce an AB number. So again, this is perfect for Geomet and variability test work. But yeah, can't produce the A and the B individually, so it can't be used in any modeling work. So, but we've used it in many cases for I guess internal geometallurgical projects with a great deal of success. Look, the last test, well, I guess method I'll show is the EchoTip method. So look, this method's been shown to be quite effective in assessing ore hardness down all the drill core. I guess it was first tested in the resource space during the Amira P843 Geomet project to provide a quick and easy, non-destructive method for continuous methods of I guess call it surface hardness. So what it is, like a pen type device, which you go along down your core to get a surface hardness measurement, also called lead hardness. This device itself came from different industry to test the hardness of various materials. So it was decided to test it down core, and it does seem to work quite well. There are a lot of measurements that do need to be taken. Generally, it's every 2.5 centimeters a reading is taken, so there is a lot of data that is collected. But like I said, it's good for determining, all right, is this bit of core, is it hard or not so hard? And obviously, if you can relate that to a bond result or AB at the end of the day, it'll prove it's a very cost-effective method for domaining, and we've done that in a couple of projects as well. So at the end of the day, we've got all this test work results, which is all good. But like I said, the aim is to basically transform that into a throughput number and back into the block model. So, all the tests that we've sort of gone through can do this with some structured analysis. Sometimes it's not so easy. It all depends on what data you have at the end of the day and how much from all the test work, and obviously what data is in the block models. So yeah, just on screen, just got a couple of simple but effective models that we developed recently with a client. And, after doing quite a lot of test work, we obtained a whole heap of AB results from the JKRBT Lite and the Bon Bor Mill work index from the JK Bon Bor Mill Test to develop these pretty simple hardness equations related to parameters in the block model. And this is essentially what you want to do with all your data. For this operation, it really came down to just being a copper assay equation to describe these all parameters. But the key thing was, this was done. They're simple, but they have quite good confidence. So when you're talking about a Bon work index plus or minus 2 or an AB plus or minus 10, that worked well for them. So at the end of the day, yeah, very simple but effective. And obviously with those ones, we use JK SimMet to be able to predict what the actual throughput would be through their circuit. So yes, you can take the AB and the Bon Bor Mill work index and attribute that back into your block model quite easily if it's done with copper assays only. But then yeah, the throughput can then either go with it or be used outside by the engineers. All right, so yeah, that sort of brings us to the end of this webinar. Sorry, I might have glazed over a few things, but just a few sort of key takeaways, I guess, from this one. I hope you will all take. Obviously, hardness means different things to different people. So when you're talking to people, ensure you're on the same page of what you want. Comminution tests have evolved over time, I guess very slowly. So, but ensure you do choose the right test for the application you are considering. So if you're doing design work, make sure you use bankable tests. And if you're looking at more assessing at the variability side of things, look towards some of these Geomet style tests. And remember, they are cheaper, but you need to do quite a lot of them in order to get some decent confidence out of it all. So yeah, look, next month, like I said, there'll be another webinar late August on the actual laboratory test work. So probably getting into more details about the methodologies themselves. So if you would like to hear more about them, look, again, please register on the website, similar to what you did today for today's one. And hopefully we'll see you there. So yeah, again, brings us to the end. Thank you all for your time.